Okay, perfect. So I got it all. Okay, sorry for the technical difficulty. So yeah, so this year our project for sure is called Taggy. It's an interesting name that we came up with. So just a little overview. So we'll just introduce the team a little bit, and then we'll go more about the rocket construction and rocket overview and concept of the project. And then we'll talk more about the systems and testing, and if we have, and then we'll go over some questions and whatever you would like to discuss. So just a small fee structure overview. So we have our so I'm the president of Andre, and we have our sub team. So we have project management, we have mechanical lead, safety, and electrical lead, and basically we also divide into subgroups, and with me I have our lead and some of the subgroups and the subgroup leads, and we'll go over the rocket and so yeah, so we can go into vehicle architecture. So I will let our mechanical lead start with that. So yeah.
So here let me recommend the present configuration. So once the configuration, we have the payload or changes or separation one HTTP, or even K and or
Just to be a thing in here. Yeah, so just to give you some background, in the past we were doing boosted dart configuration of the rocket. So basically, we would have a booster with and the dart. So it would go until water burn out, and then the rocket would separate and continue, and the dart would continue coasting to our RPG. But so last year we were trying for the first time on 30,000 feet, and we found that this configuration is a little bit too complicated for this application, and we uh, came back to sort of simplify the overall design of the rocket into just one single stage design to reach 30,000 feet. And yeah, so I will let Maxim, our ASM propulsion lead, go more into the design breakdown of the ASM.
So the airframe is completely cast. We bought everything from Wildman. Everything is made out of default fiberglass. It is a 5-inch diameter rocket. The weight, that number is not correct, it's going to be 80 pounds. And then it's going to be around 45 pounds without the motor. All of the dimensions that you see on your screen are correct. Nose cone 27 inches. Nose cone is Avon Farnham nose cone shape. We'll have 3 body tubes, 3 couplers, 4 bulkheads, and then 3 center rings that will send through the motor tube in the lower booster. In total, our rocket is 97 inches. And I don't know if they can see from the webcam, but we have the rocket in front of us right now.
Yeah, so we'll, after presentation, we can come back and show you a little bit what we have in the sector. So get that idea. So here's the third overview of our concept of operations. So I'll let our colleague go over.
Okay, so for our comma, it's a pretty typical one. Initially, we'll have a liftoff phase. After 3.5 seconds, the motor will be burnt out. Once we reach our apogee at 44.2 seconds, the separation will occur, which uses the ejection system, which ejects the rogue form parachute as well. After some time, when we reach 1,500 feet of altitude, the intended descendants for the reefing system on our parachute will deploy and allow us to expand to our main form, which will lead us to our touchdown.
And
Yes, very much correct. We use the rule of thumb of 3 times the length of the given section for shot.
Um, so, yeah, like I said, we have our rocket in front of us, so we can just, go over some of the, so you. So, yeah, so, I don't think so, our, to- so we are very complimentary about our general airframe, but I will ask them to explain and how things structure. So, yeah, actually, if you want to go, but from the top to the bottom.
Okay. On the different sections of it. So I guess top to bottom, we have our nose cone connects into a 5-inch shoulder for the upper tube, which will hold our payload here. That is mounted to a bulkhead permanently epoxied in. In the same tube, we have our air tube that is stored within here. Following that, have our isolation bulkhead that separates the parachute from the avionics bay so that the ejection system, once it detonates, it does not damage the avionics bay. Following that is our, I guess, avionics tube, which holds the avionics bay and our air brake. Followed by that is our main load booster, which has the motor tube, centering ring, and then all of our fins at the very far right.
Just about one, but open.
So yeah, I guess this is one drawing, like I just mentioned, 5-inch shoulder on the nose cone. It is permanently epoxied all the way inside the nose cone, so it can't move anymore. These two joints will be fastened with 3 weld nuts, 1/4-inch steel weld nuts, perfectly 120 degrees all the way around. We have the payload mounted to the bulkhead with 1/4-inch bolt. Right here is our separation point. And this will be fastened with shear pins that were determined by our recovery branding so that they can shear off with our specified injection card. We'll be using 3 shear pins. Correct. It's 449 shear pins. Next, we have the isolation bulkhead. There's a permanently epoxy bulkhead with the eye bolt. This side will be fastened just like the nose cone with another set of 3 1/4-inch steel weld nuts. Following that is our avionics tube / air tube. There's another permanently epoxy bulkhead, which will fasten both the avionics bay and air brake onto the same bulkhead. That as well will be fastened to the load booster with another set of 3 1/4-inch steel weld nuts. We've been using wet systems, epoxy. There is silica filler. Um,
Yeah, so,
this year we are doing, 6-tip carbon fiber fins. We still need to do some sanding, but this is pretty close to its final form. They are, biconvex airfoil fins completely carbon fiber with 3 layers of carbon fiber tip to tip on top. And it is all transitioned into the airframe. Um, Inside we have the motor tube. We have center ring positioned forward of the fin. And then another center ring about right here. About there. From that center ring to the very after one is still not installed. This will be installing the rail blocking with accommodation with the after ring. That will be epoxied in there, and they do have inserts so that the motor retainer can be fastened into it. Here we have locations of our center of pressure and center of gravity. It's just temporary, just so we can see it visually. But besides that, that's basically it for the airframe. So yeah, our fins, we have a safety factor of 1.56. That is using FAG rocket known as fin flutter calculator. That is why we're using tip to tip, so we can have the required safety factor of at least 1.5 for competition. And we did do a test to determine our gear modulus of our composite. We did some tensile testing, and then we used the Poisson ratio to get the gear modulus. Our fins have a gear modulus of 667,000 psi. That gives us safety factor of 1.57. Airplane. So, and I guess I could talk about where the rail run will be. So we'll have one very aft of the little booster. We then have one about in between the center of pressure and center of gravity. And then the third and last one will be in the parachute bay. The inside of the rail run will be smoothed out so that the parachute do not etch onto it. Everything will be epoxied with a layer of fiberglass on top. Yeah, and that we talk about recovery, yeah, I will going to mess up all of my systems. For this year, we are in the parachute system. Maybe differing point from last year, if it's not a re-severing system, or going back to a more well understood tender to center method. So the example I like to use is the belt flag. Use the belt tightening your pants, to release the belt loop. First, I'll go over the avionics bay. So this avionics bay was designed with storage batteries in mind. I have to refit the sled because of a slight support error. But 2 9-volts will go into a sled that will be inserted into this point here, and will be fastened down with 2 440 screws. Inside of here will be the LiPo battery powering the GPS. Also, a cover will be applied on top, fastened into 2 440 screws as well. On this space, there's room for 3 key switches, one for each altimeter and then one for the GPS, so that system is independently powered. On this space here, we'll go one altimeter and you can get but the key insert in. So one altimeter, a secondary altimeter, and then our GPS. This wall has been shortened to ensure that the least amount of interference with our GPS will occur. The big concern that we discussed with Rob in the past was having enough support for the separations. So the double that Rob and I know the rest of us discussed. Yeah, so To prevent the parachute from snatching the exterior bulkhead from the rocket, this is only held by epoxy. We did install a coupler, type of coupler, so it adds more surface area to prevent it from being pulled out. So that is on both sides of the parachute bay, I guess. So also mentioned with the avionics bay and the airways electronic side of things, both of those will be mounted on either side of the bulkhead, so it'll be avionics bay and then the air brake section of things, both of the same bulkhead, but opposite sides, and do the same hardware. We've already tested these things and made sure that they should work. Moving on to our transport section, you can rule of thumb of one of the body length that you're considering times 3. We decided to go with a singular length of shot board this season to minimize our capital volume. So let me see. Everything. The choice of tubular shot board was made so we could snake our wires through the shot board using a quick primitive process of inch-worming the wires through attached to a threaded rod. We added plenty of extra slack. I believe I've added 20 inches of extra slack to the wires to ensure that they will not be removed from the inserts, the male and female flanks of the wire. These will only be on one side of the shot board leading up to the centerpiece, because only one side will actually need to be in contact with the altimeters and the tendon descenders, which will be linked in series. You can see here both of the tendon descenders. One will be linked here, the other one will be linked to the other tendon descender, but also to the reef parachute. So to ensure that separation of these tendon descenders does in fact occur and can deploy to me. Ensuring that instead of having them in parallel, only one deploying, instead of both units deploying, we discussed this formation a bit more with Rob to make sure that we will deploy to make instead of staying with the configuration. For our parachute, using ripstop nylon, we constructed this parachute for tier properties. Using red, white, and blue, white for filling material, red for visibility in the sky, and then blue for visibility on the ground. I went for the best combination based on some color research to see which would be the most visible in the desert. We know last year we did problem with selecting purple, which kind of all gray, white, so it's not visible from, it's not very good visible from like that. Going through here, you can see that we have our reefing line snaked in and out of the parachute. So between sections, the reefing line is inside of the parachute, but the reefing line is on the outside of the parachute for the line section to ensure that everything fits inside. We'll be tagging it sort of as a star, if you can imagine a fork set. It will look sort of like that before packing, so we can eventually fold over and have an order to a reefing line to reduce the risk of all of the reefing lines also been tied and will be tied or will be attached directly quickly that connects to the very center of the shot board as well as the tendon defender. All of this in order to make sure deployment does occur properly.
So as far as for electrical recovery, right now we're going to be using, or we are using within the rocket, 2 RRT3 altimeters. Currently we have tested 6 in pressure chambers, and all 6 have passed. The way we did that test is we connected we programmed all of the altimeters to a certain pressure, took that pressure chamber up to that pressure, and released the pressure from it. Upon the release of the pressure, we had an LED connected to a breadboard to the altimeter. The LED would indicate that it sent or received a signal from the altimeter at the pressure. All 6 have passed. They're able to be programmed and send out a signal from the pin. Now, I wanted to do flight testing on them, so we did an L1 flight test with all the 6 of them. 5 of those have passed. One altimeter has been ejected from the competition ready file because we're having trouble powering on, and we would much rather not have that within the competition rocket. All 5 altimeters have recorded data like each other. However, the issue with this is that the pressure hole in the L1 rocket was not big enough to actually get the pressure from the outside similar to what it is from the inside. But all 5 were recording the same data, so that means that they're accurate to one another. Our next test on our altimeters is that we want to do a dual deploy test with L2 rocket with L2 motor, so higher altitude, farther recovery, as well as the actual functionality of it with an ejection system. That's planned for mid-May, and depending on the performance of these altimeters, will determine whether they will go into the competition ready time.
Yeah, about, yeah.
And then as far as for our GPS, we're planning on using a featherweight GPS. We've tested these GPSs within the same launch or L1 launches as the altimeters. We tested out 2 of them. Throughout the duration of the flight, we had good connection to each other, or to the ground station and to the actual GPS. Inside of the avionics bay of the L1 rocket had 2 threaded rods. We did this perfectly, and we wanted to see if the threaded rods would have any sort of interference to the GPS whatsoever. We did not have any interference with the GPS, however, that was 1,400 feet. We are planning to do another test on that dual deploy one in mid-May to see if we can get interference on the threaded rod at farther distances and a higher altitude. For the battery being used on the featherweight GPS will be a 2 amp hour 1S LiPo battery. I am aware that Spaceport America has changed out their rules applying for next year. To any LiPos in the rocket has to be used or cannot be flown, but it does say within that rule that if the manufacturer of the device recommends you use a LiPo, that you are allowed to. So we're planning on using it for this year. As for, my apologies, I didn't cover this in the last slide. For our altimeters, we're planning on using 9-volt batteries powered. So, yeah. Yeah. As well as with the Federated GPS, we're going to be operating it within the 900 megahertz band. So that will be something I will be request coming closer to company.
So, yeah, again, lastly, we'll talk about our payload. So, let's see if we can come back to the camera and see what is happening. So, yeah, so I'll let our payload use so the payload is made out of rolled steel. This is payload for just the metal, no electronics or mount is 99 pounds, which is above the recommended. Payload is going to contain the switch mount, the camera mount, so that we can get live feed from the rocket, a battery mount, and then the pyramid board mount, which is going to be sitting on top of the antenna. The battery mount is going to be holding 4 battery, 4 of those 9-volt lithium-ion batteries. The camera is a Raspberry Pi 3 with a wide angle lens, and then we're going to be using Raspberry Pi 0W for the camera for the set. This is the battery. This is the battery mount.
There's a cover that goes on top. There's this bottom plate that is slotted where we can access the terminals. Um, and for wiring, and then we're on the side going to have a battery control. The payload itself is attached to the um, rocket using 3D bolts on the inside. The center one is the cycle for the parachute, and the two side ones are just for mounting. Safety factor, we did a hand calculation, so safety factor that we screws on the sides that support everything. They are 10-30 seconds, torque screws, with countersink head. We did those calculations using the upper payload dashboard, and we got a safety factor of roughly which is well above the safety factor.
So I have here a prototype of our PCB and thread board that we have designed. What it's going to be doing is we're going to be having two IMUs, one 9-axis IMU, one 6-axis IMU. The extra 3 axes on the 9-axis will be a magnetometer. The other 6 on both IMUs will be gyroscopic and acceleration in XYZ and rocket roll. What we're planning on doing is recording the actual acceleration in XYZ and the angle of attack of the rocket throughout the duration of the flight. We're also recording altitude through barometric pressure with an accuracy of 50 pascals for 0.0002 ATM. Our plan for this is to record flight data, how we flew, and be able to analyze that for post processing, saving all data on an SD card. On the receiving end of this, we will have an SD, which is our wireless communication device. Whatever data is being recorded on this board will be transmitted out to a dashboard receiver on the ground. That will be transmitting around 900 megahertz band again. So I will need to request a second frequency transmit on. We're also going to be having a SAM 1010Q GPS, the same GPS chip that is on federated GPSs. That is not going to be transmitting on its own. There's only going to be one transmitter on the board, as well as a transmitter from the GPS federally. So after recovery, we're going to be able to take the board, take out the SD card, and put that SD card within the simulation that we are making using a vector machine to actually plot out in a 3D view how our flight was for the sun.
Lastly, one more thing that I guess that I'm here to talk about it is our Avery. So we do have Avery on the rocket, and we're using those to slow the rocket down more precisely to the desired altitude. And yeah, so we've done some analysis, experimental and the theoretical. Also, we are using, we are working on software and hardware for the A-Rate, very, but so, I guess, we will let you, if you have any questions, start first and then we can start some any discussion, but this is basically our overview of the rocket and, yeah, I will, open the floor for questions. So those are in progress of being manufactured, and we actually planning to have them done by Wednesday next week. So that is because we are waiting for being the last part for those, and those should be uh, done like Monday or Tuesday. Actually. So get pretty close to being done.
The working group has been really
Even done like infected. So yeah. Yeah, so we're currently planning for 27 students and 2 advisors. So, yeah, so we already submitted the pre-registration form early, and all of them were paid for, so we are ready to go. I don't remember exact number out of the top of my head, but I think it's like about 15 people, yeah. Oh, yeah, feel like we do have a spectrum. We may be-
Uh,
No, Joe left in the good number.
Our FPG right now is 30,800 feet.
Good number.
That's without air brake.
Right.
uh, how close to competition should we request that we transmit on, as well as what is the frequency between transmit and receive?
Yeah, so we just finished finals. I know some of the members are taking summer classes. So, but yeah, so far we have more time. We're trying to get everything ready, and so. Right. It is working closely again with Nido that are manufacturing the stuff, so. Which is, this is the plane that we like, we just like, I don't, hundred percent. We do not have a 17-foot competition rail. We do have a sample rail, but no, it's like half the length of a rocket. Right. The one trying to do the eagle, like one of those triangle, like experience, right? Like really long one and trying to put it on a tube to have a pretty straight line. Yeah, we're trying to pretty well get it up straight.
We have a long one right from down. In that car.
Yeah. Like you're talking.
Yeah. Typically, the ones we need that one.
Yeah. Yeah, yeah, I believe I thought wonderful. Okay. It looks like